this video we will be dealing with the MaNGA Stellar library catalog file, the MaStar all file. I will show you the downloaded file and I will provide the links in the description as well. And just let me quickly open it up. This here is the file that we will be using. I will just copy its name. The file is of FITS extension, and to open the FITS file we will first need the Astropy library, and we can use it like this from Astropy FITS, and then we can store the data. The extension that we will be using for the FITS file is the Goodreads file, which is the first extension by Python's convention, or the second extension if you go by the natural numbering. So in that case we will take it as 1. Now we would like to know what the fields are that we will be using. So to that we will open the header file, and as you can see there are a bunch of fields. These are all provided here that we can use. Among them we can use the first that we will be using, that is MaNGA ID, which is the ID for the star that is in the survey. Then we have the input log G and input TEFF, that is the log surface gravity and the effective temperature of the star. Another field that we will be using is the input source, which will give us the name of the survey from which the source is coming. Now these two fields I was also intending to use, but before making this video I checked these fields. This contains a lot of missing data, so we will not be using these fields. Now let's get the data from these fields. Okay, now that that data has been loaded, we can check that we can check them one by one by typing in the names. As you can see, there are some negative values in them, in both of these. So the first thing that we will be doing is to get rid of these values. To ease our calculations further will be to convert this data into a data frame, for which we can import the Pandas library. Now it is not necessary to import the Pandas here. Since I am going with the flow, I am importing the libraries as is. So let's get the data into a data frame. Alright, now you will see that now as you can see that the data has been stored in a row wise manner, which we obviously do not want. We want it to be column wise, so that we can give the columns name and then we can work with the data. In order to change the data frame from row wise to column wise, or to take the transpose, we use the .t. Now if we execute this again and check the data again, we can see that the data has been changed from row wise to column wise. So now let's give the names to our give the name to our columns in the data frame. Now as you can see, we have all our columns labeled. Now in order to get rid of the data that has these negative values, what we can do is we can create a filter. Again, the naming convention is just my own. There is no need to add these underscores before your variable name. You can use whatever you want. This is just how I like to do. Oops. So what this filter is doing is that it is picking up the effective temperature values where it is greater than 0 and the surface gravity value where they are greater than 0. It is obviously that the effective temperature of the star should be greater than 0 and the surface gravity of the object as big as the star should be greater than 0. So there is no problem in taking that data. Now one thing that we can notice again is that the index for these values is very not good, so we can drop this index and remove it from the data using the reset index command. We will drop the index and we will do it in place, so we do not need to write an additional command. Now if we open the data frame, we can see that the index has been properly resetted. Now a little thing that I would like to do to the numeric fields of my data is to change or rather is to give them specifically the numeric type. Whether or not the data frame has the numeric type already, we don't know, but we need the data to be of numeric type. So what we can do is to change the type. Oops. To numeric of what we can. Now this here, as you can see, that setting with copy warning, this warning is rather not um, too much warning thing. It's just a suggestion that you use the location factor, which I have not gotten around to how to use it, so I will use this same technique. But in order to minimize the warnings that I have been receiving, we can use the warning library to filter out the warning. I will so first let me just convert. We can import the warnings module and we can turn the warnings dot filter warnings. So now if I run these commands again, it will not give me any warning and change the type of oh sorry. Now it didn't give me any warning, and now it has definitely changed the type of my numeric columns to numeric. Whether it was already there numeric or not doesn't matter. Now it is definitely numeric. It is just an optional step that I took for my data. It is not necessary that your data has to be converted to numeric. Usually the data is numeric in the pandas data frame. It is just for precaution that I wrote this data, since I had problems dealing with this data earlier. So now let's get to the important stuff. Now we need to since we have the data, we need to describe the data statistics. What is the minimum, the maximum of the data, and other stuff. So for that we will statistics of effective temperature of the MaStar catalog. So the first thing that we will be doing is to check the minimum temperature of the star that is available in the catalog, which can, one thing to notice here is that I am only taking the statistics for the effective temperature column from the data frame, so I can ignore rest of the fields for now and only focus on the effective temperature. Similarly, for the maximum value I can do this, and for mean I'll have to import another library, which is Numpy. It is a pretty standard library. So in order to calculate the mean, we can do this for same for the effective temperature, and in order to use the median or get the median, in order to get the median, we can again, alright, we can also get the number of observations from the data, which we can simply do by taking the length of the data stored. For variance or for standard deviation, we can use again the Numpy library, and for for variance, we can either use the Numpy library or take the square of the standard deviation, but I rather use the Numpy library directly. And another thing that I would like to see from my data is what are the quantile values for 25%, 50%, and 75% of my data. So in order to get the quantiles of the data, since there will be 3 values, I will be storing them in the list. I can iterate through the values of the quantiles I need, and I can store quantiles dot append. There. What it will do is that it will take the quantile for whatever the given I is here, and it will append the quantile to this list here. Now let's first check the values. It will not print them. Let me just print all these values. Oh, so as you can see, we have here the statistics of the effective temperature from the master catalog. We have 2306 observation. This is the minimum value, this is the maximum value, the mean, median, standard deviation, variance, and these are the quantiles of our 25%, 50%, and 75% values from the data. So the same things can also be obtained for the log surface gravity values, but in order to do that, we will again need to write all of this code. And in order to not do that, what we can do is to write a function in another file. Here I will call MaStar all functions.py. Now what we can do is we can write our functions here, and then we can call these functions back in our working with MaStar data. So let me just really quickly write a function. Okay, so this is the function that we have defined, and then we will calculate the minimum, maximum, median, median, number of observation, and all these quantities, and we will be printing them prettily using this print function that I have written. So now let's use this. Let's first execute it so it is in our scope. Now we can remove all of this, and we can do import master. Oops. As you can see, it is successfully imported. Now we can do is MaStar all functions dot data statistics for the data that we need. Now here we can see that these are the statistics for our effective temperature parameter. The same thing can be done quickly for the log surface gravity, which we will execute. Then this is these are the statistics for our log surface gravity parameter. So now the first thing that we should do is to check the histogram. But in order to draw the histogram, in order to plot the histogram, we would need another library, that is Matplotlib, a very standard library indeed. So the standard way to make a histogram is to just use the data and to give the number of bins here. Let's first go with 64. So as we can see, it gives the detail of the histograms here as well, and then it plots the histogram here. The minimum is 3276, which is again the minimum that we have seen here, 3276, and the maximum 8770. Again, where is it? 8770. So now this is pretty standard. Now in order to make it a little bit more decorative, we can add the X labels, we can add the Y labels, we can add the legend for the data. Let me do it really quickly here. First I will let it stay on the top, and in order to add the X labels, we can do the effective and in order to add the Y labels, so we will just write these commands down again here real quick. Another thing that we can do is to add a kernel density estimation plot. The y-axis will not line up, so we will need to switch to the other axis. In order to do so, what we can do is we can use the twin x command. Now this command will add another y-axis that will be using the same x-axis for the data, but the plot will be made on using another y-axis. Now the kernel density estimation plot can directly be plotted from the data frame or the data frame column, and if we will be using the same technique. We will call the data frame, and we will plot the kernel density estimation plot. We will be using the red color just to make it different. So as you can see that the kernel density estimation plot mimics the histogram as it should be, but it kind of screws the x-axis a little bit. If we use the tight layout, so we can see it is better to plot the density on another axis rather than on the same axis. As we've done before, we're gonna plot the histogram and the KDE plot for the log surface gravity as well, and to do that we will again turn these commands into a proper function that we can use easily with the log surface gravity. So we have made our function here, and we have adjusted some things. We have set the other y-axis that in which the density will be plotted. We have set the limit to start from 0. I'm returning the x minimum and x maximum values for the limits, so that these can be set properly, because as we have seen that the KDE has some extended lines on both side of the axis. So what I'm going to do, a little bit change here, is that I'm going to return these values so that we can use it later in some other plots that we will make. So I'm gonna return the x minimum and x maximum value. Now to import these changes into this file or this Python script, we will import the master all functions again, so that our all functions that have been imported for this specific script are now up to date. Now if we will run these two commands, we can see we are still receiving the histogram and plots, and if we check x, we also get the minimum and maximum values for both of these parameters. Okay, obviously these are a little bit off from the minimum and maximum values. That is to be expected, since the histogram is not exactly made on these the boundaries of the histogram are not exactly made on the x minimum and x maximum, to give space, a little bit space. So that's okay, that's to be expected. We have a negative value for the x limit, that's all right. As I said, that we will not be touching the MaNGA ID column in this specific script, but we still have not used the source name. Let's just, for the sake of convenience, let's check what is in the source name. Let me just thin it down to the unique values. Okay, we have the surveys from where the data has come, the apogee, the Lamost Canon, and others. So the next thing that we can do is make sort of a count plot type histogram that will tell us that how many stars we have from these different surveys and in what temperature ranges. For this we can use the displot command from the Seaborn library. So to use the Seaborn library, we are going to import the Seaborn module as SNS, the standard way of calling it, and then we can do the displot. Let me do this in the console first, so it will show you what the requirements are for making the displot as well, and then we'll come back to the editor and we will make our changes as necessary. So in order to make the displot, what we need is the data, which will be obviously the effective temperature, and the source name. Oops. Okay, we will use the effective temperature as the x-axis, and now we can use the y, but we don't need y. We need to know that how many of these belong to which category that we have seen in the source name. For that we can use the hue parameter, and we will call the source name here, and then to make it properly adjust between 0 and 1, we can do the multiple equals to, fill argument. Sorry, it should be in double brackets, since we will be using the columns as a separate data frame. The error that it gave was the key error, that it could not find the t effective and the source name keys in the data frame, and in order to avoid this type of error, we have to enclose it in another square brackets for it to behave as a separate data frame. Now if we do this, we should get, and yes, this is the displot using the count mechanism. We can see that it has normalized all the values from 0 to 1, and it is sort of a proportionality histogram to all the different sources by which we can categorize the data.
as presented in the source name column of the data frame that we have passed it into. It is straightforward, so we do not need to make it into a separate function in order to use it for the log surface gravity. We can just copy paste this command and we will be done with it in a moment. Okay, this should give us the plot of the log surface gravity, and here we have that. And as we can see, it has again color coded the surveys that we have given it into the hue parameter, and now it is giving us the relative values for each of the survey in each of the log surface gravity bin. Now we have seen the histogram, we have seen the disk plot for different surveys that are present in our data frame. So we've seen the histogram, the KDE, and the disk plot so far. The disk plot was again color coded using the source names present in the catalog. Now we can next check our data for any possible outliers. We can do that using box plot. Now there are multiple ways to go for the box plot, but we're gonna stick with our data frame, and we will use the standard box plot method for the data frame now. So in order to make a box plot from the pandas data frame, what we can do is we can go for plotting. Oops. Plotting box plot, and what we can do, no, let me just go to the console first. Plotting dot box plot. As you can see, we can the advantage of using a console is that we can see what different arguments we need to pass. So first we will pass in the data, which will be our data frame. Then we will pass in the column for which we are going to make our box plot, that will be the effective temperature. And the standard method of plotting a box plot is that it is vertical, but we do not want that, we want it to be horizontal, so we will pass the vertical as false. And here we have it, we have our box plot. And as you can see, let me just as you can see, there are plenty of stars or plenty of data that are outlier in the effective temperature category. The standard range is from minimum to around 7400 or something, and the rest of the data is considered outlier by this box whisker plot. Similarly, we can make the box whisker plot for the log surface gravity by just changing this column. And but unlike the effective temperature, we do not have any outlier here. Okay, so let me just copy this command here real quick. Now another argument that I will pass here is of the figure size, so we can see the box plot a little bit bigger or wider in this case, since the box plot was really short. And to adjust it again, we can use the tight layout, but for that we will have to import the standard plotting library. And now it should give me a tightened layout for the box plot. Yes, we can do the same with the log surface gravity. We just need to change the column from T effective to log G, and it should in principle give me the box plot for the log surface gravity. Just in case, we can also make the box plot separately for each source name provided in the catalog by providing an extra argument of pi in the above plotting procedure. We will just copy it again, and we will say that you need to make the box plot by source name, sorry. And if we plot it again, it will separate all the values related to every related to every survey that is found in the catalog file. Okay, and we can do the same for the log G. Oops. We saw that the log G box plot, singular one, did not have any outliers. However, there are outliers in individual surveys, as we can see here. Okay, so we have seen our individual plots, a number of plots for the effective temperature and log surface gravity. What we can also do is we can plot these two against each other. That will be called a scatter plot. We can make scatter plot by using Matplotlib that we have just imported in line number 47. As you can see, we can make a 2D histogram. A 2D histogram will also be sort of the scatter plot, but it will have some additional properties. And then we can make this scatter plot in Seaborn library as well, which will give us even more control over the scatter plot. To make a scatter plot, we will use the standard Matplotlib library. Scatter. We'll pass in the x as the effective temperature, and we will pass in the y as the log G. We will pass it the color red, and we will pass it the marker of full stop. So this is the scatter plot for the effective temperature and the log surface gravity. We can make it pretty later on. We can add axes, labels, and we can like add the legends and all that stuff. Now one thing that I would like to show here is that if we reverse the temperature axis of this plot, let me just do it in a minute. We can do now this is a pretty familiar shape for in astronomy. It is called the HR diagram. We can see, let me just pull it up real quick in the browser. So we can see that this is a pretty standard figure in the astronomy. This might be coming in the next post or in the next video, so please look forward to that. We will discuss it in the next video. Okay, now that this scatter plot is done, I talked about a histogram, two-dimensional histogram, which can also be made by the standard Python library. Again, I will pass in x as the effective temperature. I will pass in y as the log surface gravity. Oops. And for the bins, I will use the standard 64 bins that we have been using just to see. Oops. Again, as you can see, it is same as the scatter plot that we saw, but now has some color weight to it. What a two-dimensional histogram shows is how many data points are on a specific intersection of x and y values. As you can see, some areas are darker here, some are little brighter, and then this which shows the concentration of these stars, in our case, in these specific regions. Now what we can do here to sort of beautify this plot is we can use the log normal function as a normalizing factor, which will remove this dark blue area, and we can also add in a color bar that will show the concentration of our data points in a certain location. So let's do both of these things. We import the log normal and then we run this code again. We can see that the blue region that was there is now gone, and we have a color bar that represents how many what is the count density of the stars in a particular region. Okay, the third method that I talked about for making a two-dimensional histogram was using the scatter plot from the Seaborn library. For that, I will have to use console so that we can know what parameters we need to pass. For that, we will use the scatter plot. As usual, we pass the x as effective temperature, y as the log g, and we can also separate it using the hue parameter for source name, and the data we will use is the obviously our data frame. Now if we plot this, as we can see that this is the same scatter plot, but it is now categorized based on the source names present in the data frame. Okay, the last thing that I would like to try on our data is to make a pair plot for it. Again, I will be making a pair plot using the Seaborn library. What a pair plot does is it describes the relationship between the given parameters in the data frame. So what we're going to do is we're gonna make a pair plot. We're gonna pass the data as our standard data frame, and we're gonna make it differentiated based on the source name. Pretty simple command. And let me just enlarge it a little bit. As we can see that the pair plot is showing the relationship between the log g and effective temperature in this section, which is we have seen it multiple times. This is the opposite of it. It is showing effective temperature on y-axis and the log surface gravity on x-axis. However, in the diagonals it is showing the kernel density estimation of effective temperature and log surface gravity with respect to each other, separated by these source names. We can make them separately using Matplotlib and other libraries as well, but it is far easier to do in Seaborn. So thank you for watching, and in the next video we will be doing the spectrum file that we have from the MaNGA standard library, the other file that we have not touched yet. We will correspond this data that we have selected that does not have any negative values here to the spectra file, and we will then see what we can do with that as well. Thank you very much.